In this video, we're going to go over these steps of agglomerative hierarchical clustering. What we mean by agglomerative is essentially every observation is going to start off in its own cluster. If we have a sample size of n, that means we start off with n individual clusters. And then for each observation in our data, for each dot that we have, we'll calculate how far away it is from every other dot in our data. And we're going to calculate our distance matrix. And the slides go through a couple different ways you can go about calculating the distance apart two dots are from one another. These distance matrices tend to be pretty large. For example, if you had a sample size of 20, you'd end up with a distance matrix of 190 different measurements. So again, pretty large. The next thing we want to do is just merge the two clusters together, the closest in the distance matrix. Essentially, we're just going to find our two dots that are the nearest to each other, merge them into one cluster. We're not actually going to move the dots, but instead of having their own individual clusters, now they're kind of morphed into a larger cluster. I tend to think of it like an amoeba eating another amoeba. They merge together and they become bigger. Now we're going to have n-1 clusters. We'll recalculate our distance matrix for each of those n-1 clusters. So we have to recalculate d. And then we'll just repeat steps 2 and 3 until all the clusters are merged. We'll take the two closest clusters, merge them together, recalculate our distance, take the two closest clusters that are together, recalculate the distance until we just end up with one large cluster, which means that we'll end up doing this n times, one for each observation that we have. What that's going to look like is, let's say we have these 9 dots and we want to cluster them together. First thing we're going to do is find out how far apart each dot is from each other dot. So we'll start off by measuring the distance this lime green is from everyone, then this brown one is from everyone, the red one, the yellow one, the darker green one, the purple one, the gray one, and the forest green one is from everyone. So these lines are going to measure the distance apart these two are, and we just want to find the shortest line, which is between the green and the purple. Since that's our shortest line, we'll go ahead and merge them together into a new cluster. And then the question is, though, how do we calculate how far apart this new cluster is from everyone else? How far apart is this purple cluster from this green dot now? How far away is this purple cluster from this red dot or this black dot? All the non-merged ones won't change. Just the cluster that merged will change to how far away it is from all the other ones. Well, we need a way of measuring how far away the purple is from the remaining clusters. And there are several methods for calculating how far away they are or how linked they are to one another. Well, how do we go about recalculating that distance? In our first step, it's really straightforward because each dot is in its own cluster. But now, if clusters have multiple dots, what do? How can we calculate the distance for clusters with more than one observation? So there are actually going to be a couple of different choices. The most straightforward one is what we call single linkage. So that's going to measure the distance two clusters are apart is just the two nearest neighbors. And essentially, if we're trying to figure out how far apart cluster I and J are from one another, we'll take every observation in cluster I, every observation in cluster J, and find the distance two objects are that is the smallest between them. So instead of looking at the clusters as a whole, we're looking at each dot in the cluster individually. So this is where we left off. We want to link this purple cluster to our remaining circles using single linkage, which means what I want to do is figure out for this lime green one, which of these two is it the closest to. So this lime green one, it's pretty close between both of these, but we'll say this lime green one is closest to the one on top. So we'll draw a line connecting it there. And then all these other ones are the closest to the one on bottom. The yellow is closest to the bottom purple dot, brown is closest to the bottom one, red, gray, green, and black. So now these lines are the ones that are joining these clusters together, how far apart they are. And we're going to do the same thing now. We just want to find which one of these lines is the shortest. And this time it's the line between gray and green. So we'll merge those two together and create a gray cluster and redo everything again. Figure out between this cluster and this cluster which of these two are the closest. So it appears the top gray dot and the bottom purple dot are the two that are closest together. And then for this black dot and this gray cluster, these two are the closest together. So we'll draw a line connecting them. And then for these other 4 dots, they're the closest to the one down here. So we'll connect them to the closest companion. And these new lines are the ones that are going to judge how far away each of our existing clusters are to this new one that we formed down here in the gray. We'll do it again. Figure out which of these clusters are the closest. This time it's between brown and red. So we'll merge them together into a brown cluster. Then we have to recalculate how far away every single person is from this brown cluster. So the green dot and the brown dot are the two that are closest together. Otherwise, this bottom brown dot is the closest to the remaining clusters. Again, you want to find, if we're looking for this purple cluster and this brown cluster, which 2 dots between these two here and these two here are the closest. Bottom purple, right brown dot, those two are the closest, so those are the ones that we're going to use to judge how far apart these two clusters are. And we repeat it. The yellow one was the closest to the brown cluster, so we'll merge it into the brown cluster, recalculate the distance. This yellow one was the closest of these two. This bottom brown one was the closest to the other two clusters. Again, we want to figure out which one has the shortest line. So the shortest line appears to be the green with the brown, so we'll merge them together again, recalculate. This dot is the closest with the bottom purple one. This gray dot is the closest with this one, and this black dot is the closest with the bottom brown dot. And we repeat it, find the shortest line. It appears gray is the closest with black, so we'll merge those guys together. Measure their closest counterparts to their clusters. Repeat, 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 until everything's merged together. We end up with one large cluster. So that's what the agglomerative clustering algorithm with single linkage is going to do. Another choice we have is what we call complete linkage, and it's the opposite of single linkage. Instead of finding the distance 2 observations are between 2 clusters, that's the shortest, we're going to find the distance between 2 observations that are the largest. Instead of finding the 2 closest neighbors between 2 clusters, we'll find the 2 farthest neighbors between 2 clusters. And that'll be the distance between cluster I and cluster J. So if we start here, the initial merger will be the same regardless of what our linkage is. So our initial step is to form this purple cluster. I want to figure out how far away this purple cluster are from the remaining 7 dots. So what we'll do is for this green dot, I want to figure out which one of these is it the farthest away from. And green is farthest away from the bottom one. So we'll draw a line connecting those. And then the remaining 6 dots are going to be the farthest away from the top purple one. So all of those will be determined how far away purple is from the remaining, again, from the one that's the farthest away. So these are our lines that are going to determine the distance between purple and the original observations that we had. Want to find the shortest line? It's between gray and green again. We'll merge those guys together. And then now what I want to do, if I want to figure out how far apart purple and gray are, is I want to find the 2 dots that are the farthest apart. Bottom gray, top purple, those are the ones that are the farthest apart. And we'll just repeat this step over and over again. Brown with red, merge those 2 together since that's our shortest distance for our lines. And then the distance between brown and gray will be the leftmost brown dot with the rightmost gray dot. The distance between brown and purple will be the leftmost brown dot with the topmost purple dot. And then this one down here is going to be the one that's the farthest away from yellow and green. So we'll connect them that way. And then we want to find our shortest distance again between now gray and black. Merge those together. And we're just going to repeat this process the same way we did with single linkage. Find our shortest distance, merge them together. Find the farthest distance apart any one dot is from a dot in another cluster. That's going to end up being our distance apart that those two particular clusters are. Find our shortest line, merge those clusters together. Repeat the farthest distance apart. So for this brown cluster, it's the top brown with the bottom gray. It's the leftmost brown with the top purple, and then top purple with the bottom gray. That's our shortest distance. Rinse and repeat until everybody is in one large cluster. So that's what complete linkage does. There's a couple of issues that the slides cover that talk about the issues between using single linkage or complete linkage. The fact that we rely on the mins and the maxes, while they're really straightforward, tend to give non-robust results, meaning that if there are outliers, that can kind of force the algorithm to look a little funny in the end. So what we want to try to do then is maybe look at link methods that are not dependent on the minimum and the maximum. And that's what the next video will talk about. Average linkage and centroid linkage.